Localization is all about estimating the probability distribution of the state xt, which is the pose of the car, under the condition that all previous observations z from time 1 to t and all previous controls u from time 1 to t are given. To solve the pure localization problem, we assume the map is correct and does not change. Therefore, the map is also given. If we would like to estimate also the map, then we would solve the simultaneous localization and mapping problem, or called SLAM problem, which is much more complex. But today, I don't talk about this. Today, I will talk about the posterior distribution right here. Before we go deeper into math, I want to show you how we define the different input data for a specific 1D localization scenario. This means I will explain how the car is sensing and moving. I will also show you how the map looks. This example is very similar what you already learned with Sebastian. So let's talk about the map first. The map includes the position of street lamps and trees in 1D. This means we are working with landmark-based maps, which are, in general, more sparse than grid-based maps. In the 1D case, the map is a vector of the position where these objects are. Here, the map includes 6 landmarks with the values 9, 15, 25, 31, 59, and 77. For the observation, we state that the car measures the nearest k seen static objects in driving direction. So we assume that the car can detect the distances to street lamps and trees. This results in an observation list, which includes for each time step t a vector of distances zt from 1 to zt to k. It is possible that we detect multiple trees or street lamps at a time step t, or detect nothing at all. The control vector includes the direct move of the car between consecutive time steps. This means the control is defined by the distance the car traveled between t and t-1. In this case, the car moves 2 meters to the right. The true pose of the car is somewhere in the mapped area. Since the map is discrete, the pose of the car could be any integer between 0 and 90 meters. This means the belief of xt is defined as a vector of 100 elements, and each element represents a probability that the car is located at the corresponding position. The goal is now to estimate these values.